Optical 3D scanning, structured light, fringe projection. The video introduces a non-contact measuring method using active triangulation for 3D digitizing the surface of the parts, also suitable for 3D scanning of free-form surfaces. The scanning head consists of a projector in the middle of the head and the right and left cameras. In the case of scanning head recalibrating to a different measuring volume, the projector lens and the right and the left camera lenses for the appropriate measuring volume need to be replaced. During the measurement, the configuration of the lenses for the measuring volume with dimensions 170 mm in length, 130 mm in width, and 130 mm in height will be used. The camera resolution is 5 megapixels. Replacing the lenses doesn't change the resolution of the camera sensor, but the measuring point distance changes. The measuring point distance for measuring volume 170 is 0.07059 mm. The focal length of projector lenses is 60 mm and the focal length of camera lens is 23 mm. The camera angle is 28 degrees. Replacement of lenses is possible by simple manual unscrewing, respectively by screwing. The sensor unit placed on a vertical lift unit, which allows remote control of the movement of the sensor unit to defined positions required during calibration. The covers of the scanning head are placed back. The calibration panel for the measuring volume 170 is magnetically clamped to the tilt and swivel unit. The measuring volume is determined in the software and other characteristics are checked before calibration. The tilt and swivel units start the reference run and the operator manually selects the appropriate calibration panel and enter the measurement temperature. Calibration has 20 steps, which consist in scanning the calibration panel by the sensor unit from different distances and from different angles. Distances and angles are set manually with the joystick based on a precise order. During the calibration process, the scanning head approaches step by step the calibration panel, while the calibration panel position is fixed. Respectively, the calibration panel rotates sequentially by 90 degrees, while when tilted by 45 degrees. At each step, the calibration panel is scanned. The accelerated video shows the positions of the calibration panel during the calibration process. The calibration panel is certified. The movements of the scanning head and the calibration panel can be controlled manually, or the movement control is possible to automate with the appropriate program. The calibration result is displayed on the monitor. The calibration panel is removed and sticking the uncoded reference points to the measured object follows. The reference point's diameter is 0.8 mm. The reference points are self-adhesive and tweezers are used for sticking them to the surfaces of the drawing tool for production of seamless tubes by cold drawing. The nominal calibration diameter of the drawing tool, also called as nib, is 12 mm. Uncoded reference points will help in digitally linking individual measurements in other word scans. The mixture of titanium powder with alcohol is applied to shiny surfaces by airbrush. Cleaning of reference points is necessary due to their certain scanning by the sensor unit of the 3D scanner. The position of the sensor unit is in relation to the scanned object is set. It is recommended to tilt the sensor unit by approximately 45 degrees. In the software, the acquisition parameters are set, such as the reference point's diameter, and the reference point quality. The predefined option number 2 for exposure time, the high quality and full resolution was set for measuring. For rotary table, 12 steps were set for a total coverage of 360 degrees. After these settings, 3D scanning will start. The scanning head projects different fringe patterns onto the scanned object's surface. These patterns are recorded by two CCD cameras, left and right, forming a phase shift based upon sinusoidal intensity distributions on the CCD sensors. The ATOS 3D scanner uses multiple phase shifts in a heterodyne principle to achieve highest sub-pixel accuracy. Based on the optical transformation equations, independent 3D coordinates are automatically calculated for each camera pixel. In the case of ATOS 3D scanner, a point cloud of up to 5 million surfaces points results for each measurement. The image of the left camera is real-time displayed in the software and is also real-time displayed creating the shape of the scanned part represented by the cloud of points. The 3D digitization can be viewed on the screen in live mode. Green numbered crosses in the left camera image indicate uncoded reference points recognized by the camera sensor. To completely digitize the surfaces of the drawing tool, a different relative position between the sensor unit and the scanned objects is set, followed by another 12 measurements. For measurement 16, the software detected a movement with a value of 0.386 pixels, which is above the acceptable limit. The measurement number 16 is deleted. For digitizing the drawing tool on the rear side, new measurement series is created. Both sides will be transformed by common reference points. As the accelerated video shows, 36 measurements were used to digitize the rear side of the drawing tool, 3 series of scans. Each series contains 12 steps, in other words, 12 measurements. Background points are cut from both scans. The operator uses 3 points to define a plane and the plane position to cut out the cloud of points below the plane. This is followed by the merging of 2 scans, the top and the bottom side of the digital representation of the scanned drawing tool. The join of the top and bottom digital representation of the drawing tool is made using transformation by common reference points. The common reference points are selected manually and are shown in orange color around the perimeter of the forming tool. The next step is the polygonization. The option for post-processing is selected. Polygonization means the creation of a triangular mesh from the cloud of points with the connection of points into triangles. The model is exported in file format STL. The following shows the process for measuring the diameter of the calibration hole of the drawing tool. A plane is created by fitting element on the selected triangles of the mesh by using the Gaussian best fit measuring principle for fitting element. A parallel plane is created at a distance of -20 mm from the previous plane. A single section is created through the mesh of the drawing tool by the reference plane created as second. The section is resulted in 2 concentric circles. The circle inside represents the contour of the calibration hole. The diameter of the circle is measured. So thank you for watching the video. Now is the place for your questions and comments, please. My question is, why is blue light used for scanning in this case? Why the blue light was used in this case for 3D scanning and not another color of the light? Do you have some ideas?
It is not as reflective as the other kind of light.
Maybe it's have some connection with the transfer, but it's mainly about the interference. So the blue light has lower interference with the light from the outside, from the environment. So this is the main reason why in this case is using the blue light. And my last question is, what are the advantages and disadvantages of this measuring method? What do you think?
Well, the advantage is for sure the speed of the measuring.
Exactly, correct, very good. And also the accuracy in this case is relatively high. So the accuracy is about 0.02 millimeter in this case, but to define the accuracy in the case of optical 3D scanning is a bit difficult. Some standards define the accuracy. And what are the disadvantages of this method? For example, the shiny surfaces. As you've seen in the video, Scanid was a drawing tool made of metal, so it was a shiny surface, and the shiny surface must be sprayed. In this case, a titanium powder mixture with alcohol was used and was applied by a brush. So this process is very time consuming, the preparing the object, the spraying the object, after cleaning the object. So maybe this is sure one of the disadvantages of this method. Another idea for advantages or disadvantages? If no, please, for the team who will elaborate this topic about the optical 3D scanning, also put to your presentation the advantages and disadvantages of this method. So thank you very much.